So you're breaking up.
Oh, no, I was saying let's get started by that.
Okay.
So not too many people have joined, but that's okay. Sometimes they listen to it on the recording and or traveling during summer and stuff like that. So
Okay. Yeah. I'll finish up with homework too. Just a little, only a little bit left.
yeah, sure thing.
Okay. So this is the collab notebook. So just go over just the main highlights. Okay. So in demo number 3, you're asked to learn two distributions with autoregressive flows. Two distributions just meaning x and y. So we have the one dimension here and the second dimension here goes x and y, right? And so if we look at the code, it's the D3 autoregressive flow. They have two things. They have a mixture CDF flow and a conditional mixture CDF flow. So the first dimension one is just a mixture CDF flow, and we've already looked at this one, right? So what it does is the neural network's trainable parameters are the log, which is the mean of the uniform distribution. It's a mixture of Gaussian, so it's a mean of the Gaussian. Log scale is the standard deviation in in log, I guess, and then weights. So when we flow through it, all it does is you have the weights, you softmax it because it has to be 1, and then you just run it through the mixture distribution. Right, where does x go in? X goes in here somewhere. Okay, and here the mix you set up the mixture distribution with the mean and the standard deviation of variance, one or the other, and then you do the CDF, and they're just doing CDF here, just as the mapping function between x and z from the Latin from the data here to z. So CDF, which also has the effect that the PDF, the log PDF, which is the this is actually the derivative, the determinant of the derivative part becomes the CDF, becomes the PDF. And of course, the to add more confusion, log probability is actually the log probability density here. So it's not the probability, but it's the density function. And since this is a CDF, this is the PDF, which is the derivative of it, and that's what. And then we have to take the log of the determinant of the derivative, since it's one dimension. So it's just a log of the derivative. It's a little bit confusing here, but yeah, but that's how it's the standard one we already looked at, which is just a mixture of Gaussians, right? Okay, and then the second one is slightly interesting. One more. So the first dimension is just the mixture. The second dimension is D3. Let me run this one. So yep. So the first dimension is the mixture flow, and here we just x1 is x is our input data, right? It's just two-dimensional data, x. Yeah, just 128 by 2. yeah, you can just see it's just xy, xy, xy. It gets divided into two, and then the first one, dimension one, you flow the first dimension in, and then you get the z1, right? And then the second dimension is the same thing, but you send in x as conditional. And if you look at the conditional one, everything is exactly the same, except that the trainable parameters are now an MLP. So you specify the number of layers and the hidden size, which I think is 2 and 64 or 3 and 64. But the output is mean, standard deviation, and weights times 3. Oh, I'm sorry, it's 3 mean, standard deviation, and weights, and then how many components do you have here, right? So which is 5, like the components is the number of Gaussians. Okay, it's exactly the same as the other one. You know, you have the mixtures distribution CDF, and then you take the PDF log probability PDF to get the log determinant. Yeah, but the thing is the mean, standard deviation, and weights actually come out from the MLP. So you send in all the values of x, it goes into the MLP, and it produces all of these values. So yeah, here if we look at it, we can see okay, am I not here? Okay, probably not here. Okay, so you can see there's the log scale and weights, and they're all 128 by 5 because that's the output of our MLP. So each x has its own set of 5 Gaussians. 5 Gaussian components. It's 128 by 5, right? So 128 by 5, and then all of these are put together into Z, which is again 128. Right. So this is the Z2 part of it, and yeah, and so that's all that's going on in this one. Okay, that's all that's going on, and then and so we can go to demo 4. Is any questions before I go to demo 4, or everything's good?
No.
Good.
Okay. So demo 4 is almost the same as before, except now that this is not 2-dimensional, which actually the 20 by 20 dimension, the shapes data set. Okay, and this is used as the autoregressive flow pixel CNN. And if we look at how they actually do the forward pass, so they structured this slightly differently, so they don't have a flow function. So we kind of have to look at it in 2 different ways. So what happens here is you pass an X, and then it goes through the different layers, and some of these layers are conditioned. Oh, okay. Yeah, number of components. This is MassCon 2D, which is the convolution layer. So this is basically doing the convolution, but difference here is, let's look at the NNL. This is actually doing flow and the loss computation at the same time. So you send in X, and then you should get all of the mean, standard deviation, and weights. So let's see if I can get D4 running. Of course, it went out. Okay, so so for each pixel, so 10 by 20 by 20, and 10 is the number of components, number of Gaussians, right? So we can see it's number of component, number of Gaussians, and then for each 20 by 20, all of them have a different Gaussian, and then the conditional is also taken care of. So the first one is conditioned on the second, and so on. So there's a peculiarity here, is that the weights are never used, and they only calculate the determinant of the Jacobian, and they don't actually calculate the Z part. Yeah, if we look at it, the error is just this part. Previously we had let's see if I can go back here. Yeah, previously we had you send okay, and then log probability was Z1 plus the log determinant of it, right? So here, like, the weights are completely ignored. Just, don't bother with the weights, and just the log determinant is used for the error. So I think the reason might be that they're using the uniform distribution, uniform density as the base distribution, uniform as the base distribution. So for uniform, the density is always 1, right? And when you do the log probability of the uniform, which is 1, becomes 0. So you can you can just ignore the Z1 part, because the log of the density of whatever is always 0, right? So there's probably an implicit assumption that the base distribution is uniform, because in the code I don't see anything about a base distribution. That's the only thing I can think of. That's why the flow looks so weird. I mean, there's no flow, but the loss function, the negative log likelihood, sorry, looks like this. Yeah, and so it's basically the same thing as the 2-dimensional one, but this is a 20 by 20 400 dimensional one, and it's using a convolution layer to do this. Right, so all of these are still auto-regressive. So each one depends on the previous one and previous one. So you have to go through all of them. So you can see, like, you have to iterate through all of them to get sample. Just the same problems as the auto-regressive one that we have dealt with before, right? Okay, that's number 4. I think the only difference between previous one and this one is that instead of just outputting the density distribution immediately, like the of the pixel. So if it was a binary pixel, it would be 0 and 1, like a 2-dimensional. It produces now a 20 dimensional. Sorry, 30 parameters for a 10 mixture of Gaussians.
And the 30 comes from 10 each of mean and
Yep.
variance, and then what are the remaining 10?
Oh, no, mean, variance, and weights. Sorry, they're still putting weights in here, even though they don't use it. So, yeah, and I can run this real quick. I think this is pretty quick. I guess not as quick as I think. Yeah, the output is not actually the sampling can be more than binary, right? Because it now becomes continuous. Okay, we can let it run for a little bit, and I can go back. So, yep, so we were doing this. So this one's done. Oh yeah, it's here actually. So the output looks like this. It's actually continuous, and so they actually have to floor it to be 0, 1 to make it look reasonable. Okay, that's actually what it is. But yeah. So can go into demo 5, which is when we start using the NBP and real NBP affine transforms, right? So I think here's the picture. So think x1 goes to y1, x2 gets x1, and some stuff happens and becomes y2. Right, so that's the basic idea of the affine transforms from this paper. So y is just x, and then the second part of y is scaled, an affine transform. Okay, so yeah, I think this one's done. This was the grainy part. It's continuous data, and then if we floor everything, then we get the binary data out. Okay, so let's go to NBP. So it's called the affine transform here, and there's a left and a right. Left and right just means so we're back. Sorry, I should clarify. We're back to the two-dimensional data again, and so the left just means that you use the first one, right just means the second one, right? So here, this is the type, and then you build a mask, and build a mask just means if it's left, then it's just this is the mask, 1, 0. If right, then this is your mask, right? So and the point of it all here is to use the mask here, so that you have the same code for both of them. So I think it's a little bit complicated. They could have just said if left, then just do x1 and do all, but it's the fancy way of doing it here, by actually multiplying the x into the mask and doing all sorts of things. Okay, so yeah, okay, yeah. So it's a sequence of affine transformations. So you do left, right, and this is the data set. And let's see if I can. So this is the forward pass. This is our data set. And so we're given x, which is 128 by 2, right? So that's the data batch size. Then we make the mask, which is the first one is always left, so it's just a bunch of ones here. And then x is, again, as you'd expect, just the first half. Here, I think there's a slight so okay, so the learnable parameters. So there's a whole bunch of them. So it's slightly it's a bit different from the paper. So in the paper there's S and then there's T, right? That's all. And there in the coupling layers. So maybe there's other layers that's not obvious here, but you just take the you just scale x1d, take the exponent of it, and then you translate it, right? So that's what the layer is supposed to do. This one does, what it does is, so there's an extra MLP. So all of the X's go into the MLP, and it produces log S and T. So again, X is the masked values. So half of it is 0, half of it is the data. And then we get log S and T. And this is supposed to be the logged of the scale, and this is supposed to be the translated value, I think. But then there's also another scale and another shift of the translation value here. So there's log S gets another shifted again. But yeah, right now the scale and the shift are initialized to 0, I think. So yeah, so this log S will be 0, the first pass. And then this is just a fancy way of turning it back into 2 dimensions so that they can multiply it. So then the idea is just it looks like the one in the paper is X multiplies itself into the exponent of the log X, and you add the shift. But inside there's an extra neural network that computes the log S, and there's an extra tan H. Tan H to everything. So yeah, I don't know if the tan H is to compensate for the MLP so that it's increasing. But yeah, that's probably why. But apart from that, it's yeah, the mapping is, the flow mapping is like the paper, and then there's a whole bunch of those. Okay, and that's what happens here. And this is the 2 months data set, and then and then the phase data set. So there's an interesting part that I think last time I showed is this one. So this is not phase, but let's see, months, 2 months, animation. Okay. So this is the animation they made of how each of the layers affects the data. Okay. It probably doesn't have the full effect on the full screen. Okay. But this is the first one, this is the second one, this is the third one, and this is the fourth one. And so we have see, animation. We have left, right, left, right. So it's the first dimension, and it's going right, and then it's going left, and then it's going right. And what this shows is what the animation shows, animated translation shows is, don't know if it's visible from here. Yeah, it's not. So you start with your with your data set, and then we say, okay, what happens? What is Z1? What happens in the first stage of the latent space after the first transformation? And then what happens after the second transformation? And then what happens after the third transformation? And each transformation is this one. So what happens after this one? And this is all from the final model. So this movement is just to illustrate it moving that way. It's so this one would immediately move everything here, and then the second would move everything there, and the third would move everything here, and then the fourth would move it, or the fourth would move it there. But it's showing it as an animation. But it just shows what each of these transforms will do. Since this is the original data goes to another two-dimensional data, which is the latent space, and then goes to another 2D. We can see how the data is being moved around. And there's the animation for the face also. It also takes some time. Okay, yeah, it's almost the same as this one. So we can just go into the next one, demo 6. It's similar to the affine, but instead of 2D, we now have these images, but they're pretty bad images, so it's very hard to see what's going on. See. Okay, so this is the transformations. And as we can see, this is the face animation, and there's all these different stages, left, right, left, right.
So in this case, there are 6 transforms.
Yeah, 6 layers, and I think this has 6 phases. 1, 2, 4, 5, 6. So, and the last one would be the latent representation. Okay, so it can go to D5. So in this case, the masks. So the complication here is that the mask now becomes sorry, D6. The mask is now it's not just left and right. It becomes more complicated, right? They have okay, solver has something called a real NBP, and this is where what is actually going on. So here this is the prior distribution, and there's an affine and then an some sort of normalization. So this is also the actual okay, sorry. Here, this one is almost the same. So instead of MLP, we have a ResNet, and then we have the same scale and the tanh of the log S plus the scale shift, and then the mask stuff, and then the affine transformation, right? The only difference here now becomes that the mask is more complicated, right? So, and if it's a checkerboard, I think here we can look at it. Stop and rerun. Okay. Okay, here's the mask. Self.mask. Okay, this was. Yep, here. This is the mask. As you can see, this is the checkerboard. So, so the first affine will take this one, and then it will do a checkerboard pattern of which x values to which x and y values. It's because the images are 31 by 31 or 30 by 32. Sorry, 30 by 32, and then it takes a checkerboard pattern, and then the other pattern is the channel transform. Here it's on and off. So if we look at this here, where did the real MVP go? Okay, here. It's true, false, true. So if it's true, then it just means that modify top. If modify top, then you split it one way. If not, you split it the other way, depending on the channel. There's a picture of it, right? So here's the master checkerboard. Here, you'll take it by you'll decompose it by the channels. And I see how many channels it is. I thought it would be 3, but it's good. There's 12 channels, so it's probably been shifted. Where X comes in. Yep, it comes 12 by 16 by 16. So I guess the oh yeah, the real MVP does some of that stuff. I forgot. So the image when it comes here in X is 32 by 32 by 3, right? It's RGB 32 by 33, and then the images are changed slightly. Channel transformed into 12 by 16 by 16. So the dimensions are moved from here into reshaped over there. Okay, yeah, it comes from the training. So that's the basic idea. This one takes a while, and the images are still fuzzy, like barely can see what's going on. I think it should be, yeah, it's, so I don't know if it's put a new tab or, okay. Still kind of like.
Yeah, barely restarted.
Yeah, it's not, it doesn't seem useful, but I get the other ones. You can go back to the paper, the glow, which is supposed to have really, I think in this paper they say we can actually do high resolution images, and this is the images they come up with. So it probably takes quite a while to train and produce. Oh, sorry, you were cutting out.
Oh, sorry. I was saying massive compute.
Yeah.
Thrown at the problem.
Yeah, and the other thing was that they did not in homework 2. Glow is a oh, this is question 3. Sorry, this is the homework. Glow is an yeah, glow is bonus question, which they didn't really give the answers to. So I did look at some of the glow on papers with code, but
yeah, I think wasn't glow the one that either in the lecture or whatever he shows, there's a blog post that you can go and play with.
Yep.
Where they allow you to vary the parameters.
Yep, I think so. This is by OpenAI, right?
Yeah.
So they have a blog, and that's where we're looking at. Yeah. Okay. Yeah. And so the train model is that one, so you can play around with it. So okay. So that's the next demo. So so let me move on. And this is the last one. Demo 7 is the dequantization. I think it's pretty straightforward, this one. It actually comes from their own paper. So here somewhere I have the, no, this is Flow++, sorry, this is the one. Okay, this is by them, all of the TAs and Peter and Bill, I think. There is where they show the variational dequantization here. So I think that's important. So okay, let's see. Here is the one, the first one without dequantization, and it's the same thing. We're trying to fit a mixture CDF flow. This is the this is the original data. Oh, sorry, close these guys. This is the original data that they create, and then these are the different steps as it's trying to fit. And then as you can see, it gets, it has a hard time. It's fitting some things like this, and then it actually crashes in the middle because it says it has invalid values, and it's because right here, this one of these becomes NANs. So if we just try to have discrete values and we just try to fit them, and of course, it will literally think that all of your data is point mass, like it's 0, and then the CDF can't fit that. So the solution is to quantization, and do this real quick. Okay, let me do this again. Yeah, I was playing around with something, so I need to turn this off. Okay, so this is our original data. And then the idea is that now, instead of having point mass densities and zeros everywhere, we'll just have this kind of density. And we're going to try and learn this density rather than learn this point mass version of the density. And I think the main trick is to use this. Once you get X, you're going to dequantize it by, and the function is called something here. Yeah, uniform dequant. The quant is uniform dequant. So if you look at it, it's uniform dequant. I can go into it F7. Okay, and it just takes a torch.rand, which gives you a value of uniform distribution between 0 and 1. And then you add it to X. So you're just adding noise to it, right? So noise, but in between uniformly distributed in the X regions. So whenever you say, whenever you ask for X, it will actually give you something in, it will shift it around in randomly shift it in this area. So even if you say 0, I guess 0, it will put it somewhere between 0 and 1. So you can see, I don't know if you can see it, but so we have X, and then X is now, sorry, okay. Okay, so X right now is all these numbers. There's And then, so we can see 0 to 6. And then if we take one more step, so it all got increased to, 0. The first number is still 0 to 6, but then all of it got random values. So that's all. And then yeah, it works fine, I suppose. And this is the step of the training that happens as it's doing its training. And you can see the learned distribution is pretty close to the training data. And there's no error thing. Okay. Yeah, that's all there is. So yeah, and then we're at the end of this one, end of the dequantization. Yeah, this is the one that we just looked at, and that's all there is. And in homework, it was the same questions. So the first one is data set autoregressive that we did, part the real MVP one. And then we do it for images. That's also the one we looked at. And then the MVP for faces using the using checkerboard and channel filters. And yeah, and then they have another one where you try and make bad masking schemes. So instead of checkerboard or by channel, you I think this is the one, open new tab. You actually do it by like regions, I believe, or maybe this is not the regions one. Okay, yeah, but you can do bad ones and then the results are not good. Yeah, and then the bonus questions actually has the multi-scale MVP, where it's not just half goes there, half goes there. You can have just a tiny bit goes over there, a tiny bit jumps over to yeah, and then the glow. That's not implemented. Glow uses one by one what they call it, convolution, one by one convolution. Sorry, and I think I had I did look up. Maybe it's gone. View article. Okay, never mind. I think it's somewhere here. I looked it up on Papers on Code on Glow, and it looked pretty similar, except there was some convolution going on, one by one convolution. It has a little bit more stuff going on. So it has the affine, it has the ACK norm, and then the one by one convolution, and then the affine coupling layer. So there's three layers going on. So most papers just kind of followed. Most implementations follow these, and yeah. So that's all for the second homework and the second collab. Any questions?
Great.
Or okay?
Any questions, anyone? Okay, thanks, Martin. Appreciate you doing.
No problem.
Okay, with that, let's get started with the latent variable models. I will probably take you to the first 20-25 slides, kind of through the important sampling, at least to that point, and then we'll break and hopefully continue and finish the theory in the next meeting. The thing, let me start sharing screen. Let me know when you can see it.
Yep, can see it now.
Okay. So the thing about this particular lecture, and he says it, and having gone through it myself, it's a lot of math and theory to wade through. The examples come at the very end, but most of it is math, and I'm not a math nor a probability expert, more an engineer by training, but I'll try and take you through as much of what I understood. But the math is interesting, at least for me it was, or it is, primarily because it gives some insights into what is underlying some of what we eventually end up doing. So it's easy to jump to the just the implementation and the code and forget about why we are doing what we are doing. And this the wading through the math begins to give you some insights into that. So I think from that perspective, it's a lot of math. And one other comment I would have is we see a lot of math approximation techniques and a lot of things which mathematicians usually do, which I think is quite fascinating as to how they try to solve certain problems as we move along, and we'll see that. With that said, let's get jumping into it. So the point with the latent variable models, and again, the goal, the overarching goal, of the class is obviously unsupervised learning, and this is kind of the third technique, third set of techniques we'll be learning. The first was autoregressive, the second is flow models, and this is the third way, if you will, of trying to learn and in an unsupervised fashion. So what is this new way and what are some of its features? So one of the things here is we start off assuming that behind the data that we have, there is some inherent structure, which is the latent structure. And that again is represented as usual by a set of random variables. And our intent is once we have that variables, those variables are latent variables, which we cannot see, then or we don't get to observe. From that, we can figure out what our data distribution is. So that's kind of what is the source of the latent variable models. And specifically what we are headed towards are things like variable autoencoder and importance weighted autoencoders and all of the variations thereof, which are again techniques for learning in an unsupervised way. So these are kind of our latent variables, and X's is what we have, which is our input data. So far, obviously, we've been kind of in the autoregressive and flow models thinking that there is dependencies among the X's. So from X1, X2, and then X3 is dependent on both X1 and X2. Here, we just assume that there is some inherent structure in the data, and that is represented by a set of variables, which then we don't get to observe, but from which we can extract the X. So this is just an example he uses to drive home the point that if we have 3 corgis in a park, and each of the corgis were to be represented by some set of variables, like, hey, it's a corgi and it's red and white, and this one has 3 colors, the other one has 2 colors, and this one has a floppy left ear, blah, blah, blah. The point is that by assuming that this picture, that underlying or behind the picture, there are certain limited set of variables, then we hope to get back the picture if we can figure out those latent variables, which we don't directly get to observe. And why go into the latent variables? Because we can hopefully extract the data or the picture or the image, the data distribution that we want, if we can figure out the underlying structure. And hopefully the underlying structure is a simpler version than dealing with a megapixel image. So for example, if there are 20 variables that represent this picture, then from those 20 variables and by tweaking them, we hope to be able to generate or we hope to be able to figure out first and then subsequently also generate, say, pictures with more trees and 2 kurgis or 1 kurgi and more trees or 5 kurgis and no trees and things like that, right? So that's kind of the goal of getting into latent variable models. That's the motivation behind it, if you will. The other motivation somewhat is the fact that we saw in auto variable models, one of its limitations, and I believe later on there's a whole comparison of the various approaches and the pros and cons, but he just says in this case, we know that auto variable models, the sampling part of it is, obviously the sampling is a lot less fast or can only be done sequentially, and that's a limitation as well. So that's what we cover here. They're slow to sample because we are assuming dependency. In this case, we assume that the observation space is independent and is conditioned on these variables, which we call the latent variables. Now, what about these latent variables? The other interesting thing about it is, for example, one of the things that I've seen it used in places, and he gives the example of if suppose an image is only made up of, for example, spheres and cubes, then we know certain properties about the spheres and cubes. So if we know the rules, if we know the causal factors underlying these variables, then it's possible for us to utilize those causal factors. Let's say we know the color of the cubes and the radius of the cubes and the size of any or one side of any of the cubes, then we'll be able to generate the picture if we know the colors of the cubes and the spheres, for example. So that's a very specific case, but kind of to say that if we know the underlying causal factors, which are the hidden latent factors, then we hope to be able to predict what our entire image are, or what the pixels of the entire image are, or what the entire image is, right? So, but the challenges, as we'll see, is in figuring out how do we get there, and meaning from what we have, and which is only the data that we are given, that is just the X's or the various pictures that are given to us. We are mainly talking about, in this instance, as examples, images, although the technique itself is general. And the idea and the derivation that it goes through, the mathematical derivation, is extremely general. And that's another advantage of this approach as opposed to the autoregressive or flow models, where there were a lot of restrictions that we imposed on the approach, and those restrictions enabled us to simplify the math. So in this case, because we don't apply the restrictions, the math is much more complicated. But at the same time, we end up where, we end up at a point with techniques that are much broader and that are much more general. So the way to specify the latent variables is obviously still a very active area of research. So the fundamental equation, and we'll see this right portion of the diagram a lot, which is Z's are our latent variables, which we don't get to observe. And then the X's are our actual given data. These are our images in our example. And theta is the parameter, and here you can think of this Z to X as going through a neural network parameterized by theta, where X is dependent on the latent variable Z. So X is, this is X conditioned on Z. Now you can think of Z and X as vectors. The important thing also, he draws the distinction that in case of autoregressive models, in case of flow models, the assumption, and if somebody can knows the exact technical reason why, then you can, but it is the case, then feel free to expand on it, but it is the case, as we saw, that the assumption in case of the flow models is the dimensions of X and Z are identical. That if Z is of dimension RD, if Z belongs to RD, then X also belongs to RD, or vice versa, meaning if X is belonging to RD, then Z also needs to belong to RD. But in this case, as I said, the latent variable models are a very general approach, so that limitation doesn't exist. Z, as I've been giving examples, Z can be, say, 20 variables, whereas X, which is, the a megapixel image, can obviously have significant dimension, even a million dimensions overall. The point here that he's trying to say is that Z can be a variable that we can think of as coming from a Bernoulli distribution. So each value of Z can be a 0 or a 1. And then taking it through a neural network, we get to X, where there's a deep neural network of Z that then delivers X, where the X values belong to the probability distribution or conditional distribution X given Z. Right.
So regarding this restriction on flows, that Z and X should be of the same dimensionality, I wanted to figure it out if my understanding is correct. So as I understand, you can only get invertible function if the input and output spaces are of the same dimensionality, right? And so that is why we have this restriction, because we want to have an invertible flow, and that is why it should always be of the same dimensionality. Is that correct?
Yeah, I also, that's correct. But I think underlying that, all of that, is that the only way to make probability go from one space to another, so from your latent space to go to your sample space, it has to have an invertible function, a mapping. So what we're trying to do is make a continuous mapping, a continuous density, and in order to do that, you need that invertible function.
But Martin, at least in the rest of this lecture, we'll see that as we get into the math, that he seems to say, or he doesn't explicitly cover it, but that you can go from one distribution to another continuous without making the necessity for Z and X to have the same dimension.
Yeah,
so I believe that invertibility was required because we want to sample from Z distribution to get X's, and we learn we'll learn transformation from X to Z, and then we sample in the reverse direction. And to make that happen, we need invertible transformation, right?
Yeah, I'm inclined more to the argument put forth by Arto, that it is the fact that the invertibility requirement is what causes the need for X and Z distribution to have the same dimension. Because in this case, as we'll see as we go down further, that the invertibility requirement is not there. And because of that, then I believe that X and Z could be of different dimensions. There is dependency on the distribution and sampling that still happens, but the invertibility requirement doesn't exist in the latent variable models, as we will see when we get into the details. So that's why I was curious. So are you saying that without it being invertible, that you cannot go from one distribution to the other?
No, you can. It's just there's some loss and loss of some I guess some loss of
Yeah, there is.
information. Yeah, that's. But with flow,
Okay,
if you
yeah,
just
that is true.
if you want super accurate, like this is the distribution, it goes over here and it's the exact same thing. But if you don't care, if like, oh, you go here, but it's kind of about the same, I think it should be fine if you define it properly. But I think flow just wants it to be exact, like you can make everything exact. That's why.
That may be because in this case, as we'll see, we approximate the distribution.
Yeah.
And talk about bounds. It's not exact.
Okay.
Thanks, Otto. Thanks. Okay, so now what we said is the Z distribution, we can assume that it's Bernoulli, and that's what we see here. But the Z distribution could also be Gaussian, for example. So the question is, what kind of distribution do you want for Z? And there are many ways that he talks about that you can either, again, as we go into the details, we can see that you can either posit distribution for Z, meaning say it's Gaussian, it's uniform, it's Bernoulli or whatever, or we can learn the distribution itself. And typically it is, at least for most of this lecture, we'll kind of posit the distribution of the latent variables. And eventually, as we move further into the course and potentially towards the end of even this discussion, we'll begin the approach to learn the latent distribution as well. And that's the other thing which maybe it's obvious to people, but I haven't thought about it. But the other point he makes, which I thought was interesting to highlight, is for any continuous variables with finite variance, the Gaussian distribution is the highest entropy distribution. So that's a comment he made, and I thought, I mean, it's kind of obvious once he says it, but I hadn't thought of it in that way. That's for continuous variables with finite variance, the Gaussian is the highest entropy distribution. So by assuming that, you can you're starting off with a fairly broad and representative, or the most high entropy distribution as your latent distribution, if you will, right? So with that said, as an example, so again, here, what do we have? Here's kind of the structure of the latent variable models. The distribution we'll have is PV of Z. And again, as Morten has said, this is, in fact, a density distribution. If it is continuous, Z, this notation says Z is a random variable chosen from a probability distribution PV, and X is from P theta of X conditioned on Z. And this is basically a neural network taking it from, once you have samples, then you generate X going through a neural network. And the likelihood is evaluated of the P theta of X using basically, or, again, here he assumes kind of a conditional distribution, a discrete distribution, because this is a sum, but it could be an integral and that it would become continuous. That is, for every Z, you have the PZ of Z, the probability distribution, and then you multiply it by the value, which is P theta X given Z. So that's what is your likelihood. And then how do you train? You train it by maximizing the log likelihood. So you have the likelihood given here, the log of the likelihood, and then I here is, if you consider X as an image, this is over the every I that you calculate the log likelihood. So that's kind of the variables we'll see repeatedly throughout the lecture, is how do we simplify this expression that's inside of this guy, inside of the log. So that is going to be our kind of the focus over pretty much 2/3 of the lecture that we'll be going through. Now, So what we've seen a little bit is the motivation. Most of the lecture, or at least the parts I've gotten through, I will prepare the remaining of portions of this lecture. But going through most of the lecture, we take steps to first of all identify the objective that we will be optimizing, and basically, as I said, the two, sometimes what we have in our toolkit is stochastic gradient descent. So what we try and do is see how we can use that. We have a hammer, so we make the object look like a nail and use it. So it's almost, that's the feeling I got going through this, first part of it. That is, we have stochastic gradient descent, so let's convert the problem that we have into something that we can use stochastic gradient descent on in order to optimize it. And so what we try to do is figure out an objective that we can optimize. And we take incremental steps to try and make the process handle more and more general cases. So in the first instance, we'll kind of start with what is a very simple assumption and what is an exact assumption. Then we go to, but we cannot do that. We cannot successfully implement the exact assumption for in the high dimensions, and we'll see that. So we'll then go to sampling the prior, which is sampling the latent variable, which is the PZ of Z. But that's actually, again, not what we want. What we want is sample the posterior, and how do we get that, or how do we get closer to it? So we move from prior sampling to important sampling, and then even more general case but because this is complicated to do and we won't always be able to arrive at an answer, we kind of take the next general step, but then it becomes an approximation, and we begin to deal with what's the approach. But in this case, we approach what we want, but we do that through a bound. So it becomes variational lower bound or evidence lower bound. And that's what is elbow or VLB. And all of this is just setting up the objective that we want to optimize. So all of these techniques go towards that. And then we look at a couple of techniques which are actually used in order to perform the optimization. And so once we have the objective, which we derive, then we try to apply the optimization using two different techniques. And we'll discuss these techniques. And all of this is just heavy math. And then obviously optimizing the VLB. And here's where once we have gone through all the math, we kind of, then the rest of it is just, it's variations on the theme, and it's just a matter of applying what we have derived, if you will, through the first 2/3 of the lecture. And then we go into the different variations of the variational autoencoder and related ideas. So that's kind of sets up the flow of the entire lecture for this particular lecture. So let's talk then about the objectives. Of what we want to do. Let's look first at, okay, so let's first look at the Z to X. This is, as I said, the latent variable flow. And we have seen that this equation maximizing over I, meaning over all the examples of log p theta of xi, and p theta of xi is derived from the samples of pz of z and then shoved through the neural network p theta xi of z. What we are interested in is in figuring out how we can figure out this guy, right, inside of the log. So let's start with a very simplifying assumption that the domain for D, which is the distribution that we want to sample from, this guy, the latent variable Z and the distribution for it. Let's assume that it can only take on a very small number of values. So here again, we are making a very simplifying assumption that Z is the distribution for Z can only take on specific small number of values. The reason for it is so that we can exactly compute or derive this guy. And once we derive it, then the training for the whole process is simplified. And if it is exact, then obviously the objective is tractable, meaning the problem can be solved in a precise manner, kind of bringing in analytical technique. But the moment we begin to assume that Z is very general and it's in all significantly large number of dimensions, and it's not exact, very large number of distributions, then it's not possible to exactly compute this value, and we have to begin to approximate the value. Okay, now one thing that is done, and that's kind of the second step, is kind of learning the prior, and the prior is the kind of the latent distribution here, PZ of Z, and we'll kind of look at what that means and how that is done, or what does that approach entail. But first, let's start with the assumption that the latent variables are coming from a small number of distributions, so they're very tractable and exactly learnable, right? So as I said, this is the sequence of steps we'll take to get to the very general case of least amount of assumptions with respect to Z. But we'll start with the exact case. Okay, so the exact case says that our latent Z variables, we are assuming now a structure for the model, which is we say that our whatever image or whatever is made up of Z's, the source underlying what we see in the picture comes from only 3 values of Z, and the 3 values are also again uniformly distributed across 3 Gaussian distributions. So it's a mixture of 3 Gaussians, and the distribution of the values is uniform. So that means there is, Z can take 3 values, A, B, or C, and then the probability of each of them of Z taking any of those values is uniform. It's 1/3. And obviously, this is the equation for the Gaussian distribution. Assuming that Z takes value A, value B, or value C, each of which can occur with a probability 1/3. In which case, then, our training objective becomes, log of P theta of Xi, and P theta of Xi is, 1/3 the probability with the value of Z having a mean mu A and variance of, this is actually, I think, epsilon, not so much sigma, but, this ought to be the epsilon, I think, notation. But anyway, it's 1/3 Z assumed to be A, 1/3 Z assumed to be B, 1/3 Z assumed to be C. Therefore, the mean and the standard deviations being the corresponding mean and standard deviations of the Gaussian distribution. If Z were A, if the Z, or I should say more precisely, Z sampled from Z having the value A, therefore coming from PZ of Z, where it's from the distribution A, distribution B, distribution C, right? So that's done. We then, so we do what we saw in the previous lectures and what Morgan took us through as well for training the data with 3 Gaussians, of course, in a 2-dimensional space. We are keeping the space small because we want it to be exact, and we are making these simplifying assumptions. So as we start to train, assuming this mixture of Gaussians, we have kind of posited that this 2D distribution or this 2D data set, underlying it is a distribution with 3 Gaussian distributions, which mean, with equal probability, and A, B, C being those distributions, with the mu being at, mu A, mu B, mu C, and the variance, and we kind of begin to train, and you can see that eventually we fit the data pretty nicely. Now, it's entirely possible, as he says in the letter, that we may not fit this, and it can end up in some desirable state. But the point here is we have assumed the model structure underlying this data, and we have this data, so we can now maximize the log probability of each of these data points, right, to be the sum of 3 distributions, which are our prior distributions, the PZ of these, and right, and thereby figure out what eventually is, and make the values of mu A, mu B, mu C match what we see in the data, right? So that's what we have done here, and run the optimization. And as you go along, you find that the 3 Gaussians nicely cover the data. But the issue with this exact approach is, as we have said, we have posited the distributions, which we'll continue to do. But the more important, difficult challenge is the fact that in very high dimensions, this is 2 dimensions, but in very high dimensions, this approach will no longer work, right? Because we can't exactly evaluate the distribution if Z is having can have many values. So as we do, as we saw even in the flow situation, the next step we do in order to kind of proceed to, we can't tackle it in high dimensions, so what do? Well, we can estimate the distribution. And instead of exactly doing it, assuming that there are 3 and the probability of the each of the values is 1/3, assuming a uniform distribution of the underlying Gaussian distributions, we can say, well, what we'll do is sample from from this probability distribution, PZ of Z. So instead of it being an exact, we'll kind of sample in order to make the in order to estimate what the value is. So at this point, it becomes expectation. So in order for this value to be calculated, what we've done is we say we take k samples of for each of I, we take k samples, and the k is from 1 to whatever we choose as the number k is, and then we obviously normalize and then multiply by, and for each of the zki's that we sample, that is, we choose k samples from the probability distribution PZ of Z, we then evaluate the xi for each of the zki's, and that is what we estimate to be the objective. So we run stochastic gradient descent on this estimated probability instead of the exact value. Okay, so that's what is called sampling the prior, and it's the prior because we have assumed the prior is the underlying latent distribution, that is PZ of Z. We'll again get to why it's called the prior and what we actually mean by the posterior as we get into the remaining portion of the lecture. But that's kind of what we do here is we sample from the distribution, approximate it, and then for each of them push that through the neural network to get the result. Right. So in this case, for every xi, we'll sample capital KZ and then run the stochastic gradient descent. Now, the interesting thing is this seems like a viable approach, but there is a issue or a flaw in this approach. And he explains what the issue is in the next couple of lectures, in the next couple of slides, why doesn't this approach just get us to where we want to go? And the explanation it gives is that assume that we have, as we said, we have a large number of Z distributions, and assume that the Xi is at this particular point, is what we have. Now, the Z distributions are all over the map. Like we have 11 or 12 of them instead of the 3 ones that we showed in the first set of pictures. And consider that the data is clustered this way. Now, the point is, if we are taking the sampling approach here, right? So if we take the samples, then the points that are going to help us to learn the X, you can see that sampling Z uniformly results in only 1 out of n terms being actually useful and helpful for us to learn what this Xi is, right? And in very high dimensions, that is, if we think that there are like 100 high-level properties, then the probability that we'll get any useful signal from this kind of sampling, the prior, is going to be very low. It's like, 1/2, assuming the Nodian stuff, then the probability is only 1/2 to the power of 100, which is extraordinarily small. So the point or the flaw in the exact approach was the fact that we couldn't, it's obviously oversimplification and we can't use that in a generalized case. Then we went to prior sampling. The flaw with prior sampling is the fact that it, in very high dimensions, the useful signal we get to learn is very small to non-existent. That is, most of our prior samples will turn out to be 0. And that is an issue which will limit us from learning what we are after, right? So the point is that we cannot count on the prior sampling to land us on the right set of Z's, which will help us to kind of get the Xi's that we want. That is the flaw in the approach of prior sampling. Okay, and he illustrates that by saying, let's say that our function that we are trying to estimate is f of z, and what we want to compute is the expectation with z coming from the probabilities distribution pz of z of the function f of z. Now, if the function f of z, let's say, is these two chunks right at the tail of the distribution, then two things can happen. The one potential, and he doesn't get into this case because we have kind of, by choosing the correct or choosing a desired distribution pz of z to be Gaussian, we are kind of avoiding the problem. But he says there are two fundamental problems with this approach. One is pz of z, if we didn't choose the distribution appropriately, could be hard to sample from. Currently, at least, we don't have that problem because we've chosen a Gaussian, which means we can sample from it fairly easily. But we have the second problem, which is that the samples from pz of z are not very informative. And here is an example of what he says you can have, which is, let's assume that fz of z puts these at these values. So most of your samples, given it's a Gaussian, will be in this space. Whereas what you want in order to do this, in order to successfully and efficiently compute the expectation, with z being in the distribution pz of z of f of z, is you want values of z here and here. But that's not what you're going to get typically. That's, again, the same illustration of this problem that we talked about. The samples of z that you choose in the general case of a Gaussian, for example, and we choose a Gaussian for the reason that I stated earlier. It's the highest entropy distribution for a given set if it's of continuous variables, but you won't get informative samples. That's the problem. So we saw the exact approach not work. We saw the prior sampling have this flaw that we won't be able to learn what we seek to learn efficiently or in a desired manner, right? Because the samples are not informative if we just sample. So that's what takes us to the next approach, which is called importance sampling. And again, once we are done, even for me, a lot of this was new in terms of getting into the details of what each of these techniques are. So I had to kind of, in order to understand some of the details behind it, I had to dig up and wade through some YouTube videos, and I'll post a link to them of what there's quite a bit of math behind importance sampling itself, which we'll not get into, but we'll understand just how it helps us. What we want to do, as we saw in this previous slide, is we want to compute this guy. Expectation of a function of z with z chosen from a probabilities distribution, Pz of z. Okay, that's kind of what we are after. And we are after this because this structure is what is inside of the log that we were trying to, inside of the objective that we were trying to optimize. Okay, so we are still in the process of trying to give you the overall context. We are still in the process of trying to define the objective that we want to train for. And in the process of defining that objective, we are now trying to get an estimate for this expectation. And that's what we're trying to do. And we're trying to do that by using this technique called importance sampling. So what is importance sampling? So what does importance sampling do? So the problem we have is if we take a Gaussian, such as Pz of z, then as we saw, the samples we get from it are not very informative. So what we are after is in some sense a distribution that gives us informative samples. But what we are currently stuck with is this high entropy distribution Pz of z. So how do we solve that? Well, apparently there's this technique called importance sampling where, so mathematically what we do is say we divide and multiply by another distribution, say Qz of z, right? And if we can now change this equation such that we are sampling not from the high entropy Gaussian distribution, which is easy enough to sample from, but gives us non-informative samples. But if we can sample and switch the distribution that we want to sample from to Qz, which is something that hopefully we will make that distribution a desired distribution which has the properties that we want, then we can solve the expectation equation that you just have on this side, and we can kind of then unwrap the whole process to get where we want to go. So what we do in this case is we say we multiply and divide by the Qz and sum over every z of Qz, Pz, sum over every z of Qz is basically expectation of z chosen from the Q distribution. So this guy here is basically translate to the expectation. And then you can say this is expectation of that value. So instead of it, being this guy, we have now just through this technique, which is this importance sampling, and you can kind of go into the mathematical details of it there are lots of videos that cover it, but bottom line here, we have now translated this equation to this guy, where Z is now sampled from distribution QZ, and this equation inside that we want becomes PZ of Z divided by QZ and then F of Z. Now, we could then use the same technique we used for just the distribution PZ of Z, F of Z, and instead of that, we can do it here and basically translate this expectation by sampling. Right? Now, the challenge though is or we haven't completely solved the problem. What we have done though is said, instead of choosing samples of Z from PZ of Z, which doesn't give us much informative samples, we switch the distribution that we want to sample from to QZ, and then sample from that and calculate, the K samples using the Z case sampled from the Q distribution. Now, we haven't. The reason I said we haven't solved it is we still have the problem that QZ now needs to provide us with informative samples. Okay, we have just said we want to do it, so let's change it so that we are sampling from a desired distribution. But we still need to make QZ the desired distribution, which has the properties that it yields better or more informative samples than our original distribution PZ of Z, which was just a Gaussian. Okay, but this manipulation in this slide gets us to allowing us to using a sampling to get an approximate solution, but the sampling is much more informative. Why? Because our choice of QZ, which we'll make over the next several slides, is a much better distribution to yield us informative samples towards our goal. Right. So importance sampling essentially is a way to switch the distribution you're sampling from and still compute an approximation of the original expectation, right? So that in the limit of K being very large, right, we will still be correct with respect to our original expectation. That's what importance sampling helps us to do, right? So, any questions on this?
I have a small comment on the importance sampling. I think I came across this in a reinforcement learning, where where you get data from so you're trying to learn a distribution, but then the data is actually coming from a completely different distribution. So there they use importance sampling to say, okay, I can learn what I want to learn, but from a completely, maybe data that's not directly related to me, using importance sampling, right? So I think it's similar idea, except that we now want.
Yeah, it is.
Yeah.
Yeah, you're right. And he kind of touches on the similarities to reinforcement learning, I think, a little later. I haven't gone into reinforcement learning myself, so maybe I know Arto has, and maybe he or other people who are more familiar with it can yourself to more convey, and because that helps set it in context too. Okay, so the other thing he points out, sorry, go ahead, Arto.
Yeah, I just wanted to say that regarding similarity to reinforcement learning here, it's basically the same technique applied in many different cases. So it's general probability theory technique, right? And it allows you to basically reweight your samples according to another distribution. So yeah, that's exactly the same thing. That's correct.
Great, thank you.
And the other interesting thing he pointed out, which I thought was, again, insightful, is that, something that I hadn't, if he hadn't said it, it wouldn't have been obvious to me, that one thing he talks about is, let's say, obviously, they're sampling from Z, which is, or coming from QZ, right? The question now is, or if you were to ask the question, do you need more or less samples from QZ compared to the number of samples you take from PZ of Z, right? It's interesting because he made the statement that actually you find out that you may even need less samples from QZ than from PZ. And that intuitively makes sense, because if QZ is chosen to be a distribution that gives you more information, then you can obviously have less samples from here than from here, right? The other way to think about it, he kind of got into, is the fact that, let's say you sample from Q. If you sample from Q samples that are highly likely, but, or I should say, if you sample Z under QZ, meaning with it from the distribution QZ, that are highly likely in Q, but highly unlikely in P, right, under the P distribution, then what happens is this ratio will scale down this guy, right? The contribution will scale down. So the samples which are corresponding to the Xi's in a sense, right, which is eventually what we want, right, are going to be scaled down. So if the sample from Q that is highly likely, but under P highly unlikely, because remember, again, the goal is that we want it to be from this distribution, but we are sampling actually from this distribution. So if we actually take samples, I should say, which are highly likely in Q, but highly unlikely in P, then this will be large, this will be small, so it will scale this sucker down. And that will be, and because we want eventually to get to the correspondence with Xi, which is what is sitting here, right? So I think in that sense as well, the interesting thing is that the goal is to find, remember that the goal of this is to find Z's which are likely given the X's. And this kind of a swap helps us also in that case. So a couple of observations besides just staring at the math is the fact that A, it's likely that we may need less samples from QZ, excuse me, than from the original distribution, and that because this is more informative. And this whole process kind of can, if you take samples from Q, which are likely in Q, but unlikely in P, Z of Z, then this will get scaled down, which is kind of another desired property that we want, right? Now here, let me see whether it's actually on the next slide. So this is just a rewriting of the same thing from the previous slide. What we have done is we have replaced this guy inside the log with the importance sampling, where it's PZ of Z divided by QZ of Z, and then we take the samples 1 to K of K samples with ZK chosen from Q instead of from PZ of Z. Okay, now we get to the crux of the issue as well. We haven't solved the problem, as I said. What's a good proposal distribution for Q? So this distribution in an importance sampling, the distribution we choose to flip to or choose to sample from is called the proposal distribution, Q, right? And this is actually just in this setup, this is the prior, right? So what is a good distribution for Q of Z? Now, this is where the better distribution we choose, the more informative distribution we choose for Q of Z, because the whole reason to switch and go through importance sampling is because choosing samples from this distribution did not give us the information we sought. So we do need to pick a better Q. So, or a good Q. So what is a good Q? So we want distributions which are compatible with the xi, that is the x that we are actually after, given the latent variable is z. So then how about choosing a QZ, which is a p theta of z conditioned on the xi, okay? So the desired distribution we are after, which would give us the best result, or at least closer to the desired results, is z conditioned on the xi, p theta z conditioned on the xi. Now, this conditional distribution can just be rewritten as p theta xi of z multiplied by, this is just Bayes transformation, right? Z of xi, xi of z, pz of z, and then p theta of xi. So this formulation is just Bayes rule, right? So you just flip it around. Now, this guy here is what we typically know as the posterior, and this guy is the prior. So what we had looked at in the second step after the exact one was just sampling from the prior, which gives us very poor information. So now what we have done is we actually want to sample from the posterior, that is from z given xi. So if we, after implementing this important sampling switch, if we can sample from a Q, which is actually our posterior, then we are good, or that will give us a very informative samples. But the challenge now becomes, it's not very clear, how do we sample from this distribution? And so we are off to solve that problem next, right? So that's kind of what we begin to do. So the point is that in the important sampling, we want a proposal distribution, which is QZ of Z. We cannot directly use the P distribution that we want. So we propose a parameterized distribution Q that we can work with and that we can sample easily. Now, we parameterize the distribution. So until now, we're just saying this is just Q of Z. But instead of that, what if we choose the distribution Z to be parameterized? And parameterized means, like P of theta. Theta is the parameter based on which the P theta of xi given Z. So theta is the parameter that helps us calculate, the given xi's, the values of xi given Z. So similarly, we parameterize Q with variable phi, and we choose the distribution again to be such that it can be sampled easily. And then remember, though, that we still want the distribution, this distribution which is now being parameterized to be a Gaussian with the parameters mu and sigma squares, rho square. But the important thing is it needs still to be as close to the posterior. And the reason for it, we remember, is we wanted to be as informative about xi as we want, obviously far better than just the prior. And at the same time, we want it to be easy to sample from. So we parameterize it and make it a Gaussian. Any questions? Okay, so now it's essentially the same stuff. And so what we have now changed the problem to is trying to find a parameter phi that makes the distribution Q as close as possible to this guy, which is the posterior. So we've kind of gradually released the restrictions while trying to approximately arrive at the objective that we want to derive. Okay. Now, then we get to solving this problem, which is how do we choose a parameterized Q parameterized with phi. Q is a distribution of Z. So how do we find a distribution of Z that is as close to this probability distribution? And in order to obviously find two distributions that are close to each other, then we do that using the KL divergence equation. So what we are doing in this slide is we are first saying that Q of Z will pick to be a Gaussian, but we'll parameterize it with phi, and we'll choose the Gaussian such that we make this Gaussian distribution close enough to the posterior so that when we sample from it, it is giving us information about the distribution and will help us solve the original problem that we're after. Now, the important thing that he highlighted, which is again a detail, but I think it's worth making the point, is that any distribution Q of Z will work, okay, in the importance sampling approach. This additional step whereby we make Q of Z as close to the posterior as possible, what it actually helps us do is help us make the process much more efficient. That is, the samples that we take from here can be fewer and can be much more informative. So the point he was trying to drive across is importance sampling works regardless of the choice of Q. It's independent. We just are able through that approach to pick from a desired QZ. But by choosing the QZ to be as close as possible to the posterior, what we are actually achieving is efficiency, not correctness, because the correctness part is guaranteed by just the importance sampling approach. But the efficiency part is something we still care about, and therefore we try to make these two things as close as possible. Right now, the mechanism by which we make the importance distribution or the proposal distribution that we want to be close to the posterior is using KL divergence. So so KL divergence slide. Okay. So KL divergence is essentially defined. We minimize the KL divergence between two distributions, between our distribution of Q of Z and the posterior, which is P theta Z of Xi. Okay. And because minimizing the KL divergence means making these two distributions as close to each other as possible. And the KL divergence, again, for those of you who are already familiar with it, but if you want to remember it, it's basically defined as the expectation value under the first distribution. So that's this part, the expected value under the first distribution. The first distribution is Q of Z, and the expected value under the first distribution of the log odds of the two distributions. So this is your first distribution, and this is your second distribution. So the expectation of, second distribution. So the expectation under the first distribution, that is Z sampled from QZ, the log odds of the two distributions. So QZ divided by P theta of Z given Xi. That's what your KL divergence equation translates to, right? And this, these are just mathematical derivation, minimum of Q of Z, ZQ of Z, and then log of a ratio, and P theta Z of Xi from the equation, or from Bayes' equation, you can just write this way, and you can simplify the log of the ratio to be, the subtractions, but because p theta xi is in the denominator here, it goes to the numerator, and so it becomes an addition. The one other thing to notice as you go push through the math here is, while all of these values, this guy, and this guy have z, and therefore since z is sampled from qz, but this guy does not have, I mean, this should actually be all of that. This guy doesn't have any dependency on z, right? There's no dependency on z. So it can be pulled out of this expectation with respect to z sampled from a QZ distribution. So it gets out of here, and then you just do minimum of QZ of z, the expectation of z sampled from QZ, and then these three values. Now, what you see in these three values is the fact that this is a desired distribution. We know, and we have chosen it to be easy to or easy to sample from. We know that this is easy to sample from, and this is just a neural network that we push through. So all the needed quantities in this objective that we have derived is very readily computable, right? So that's kind of what we run, what we have landed up at. So if we run optimization on this equation, and we find the Gaussian mu, and we can find the parameters mu and rho square, and then make this distribution as close by minimizing this guy and optimizing that, this equation by running stochastic gradient descent, then we can figure out the answer to what we were after. Okay, which is after the third approach of doing importance sampling helps us now to figure out a training approach to get to our objective. Now, I think we are almost out of time. We can start from this point. There is one additional last step. The math behind it, again, there's a lot of I haven't dived into it of how we go from the mean field to what is referred to as amortized inference, but he does a good job of at least giving you the intuition for what we are trying to do here. And in the interest of time, we'll pick up here and kind of just touch on the importance sampling again, and then move forward through the rest of the lecture in the next Sunday. Because if we get started on it, then I think I'd like to at least take a few more minutes. We are probably very likely to run over. So we won't get cut off. I think he's provided that objective, but I'd like to stop here, and then we can start with potentially backing up a little bit and then moving forward, just so that it helps us revise and get through the rest of the lecture as well. Any comments or questions so far?
So are we, is KL divergence going to be the loss function? Do you know, or?
Not the loss function, but basically what we are after, Mochen, is to figure out the function that we want to optimize, right? And or what we want to run stochastic gradient descent on in order to learn the parameters we want to learn, and that will be this guy and one other term that we'll get to and why we need that term. So remember, what we are trying to do here is to figure out, if we back up this, where we got into this was to figure out that, way back here, we were just trying to compute this guy. And why were we computing that guy? Because we were interested in computing this guy. So, eventually we are after having done all of this, we'll be substituting this into an equation where this will become, and we'll talk about what amortized inference is, and why it's desirable, and gets us to what we want to do of getting the latent variable z given x and setting our structure up so that we can go from one to the other without all of the restrictions. And we'll figure out that the objective that we want to do is obviously this guy, T1, which is this equation, which is z sampled from the important sampling of QZ. And this is obviously our first part, right? This is what we wanted to achieve. But with another condition coming into play, which is, well, we have done this because of our desire to sample from Q, but that's not good enough, because we also want to do this under the condition that the distance or the distribution of Q of zki is very close to the posterior. And how do we achieve that? We achieve that by minimizing that. So our original objective is this, but the choice of Q should be such that it is as close to the posterior as possible. That means we also need this. So combining these two, that is, we maximize this while minimizing this. And that is our objective that we'll run stochastic gradient descent on to find the parameters theta and phi.
Okay.
So that kind of explains what the KL divergence term comes in, or how it comes into play in what we are after. And then there are, two other ways of deriving the same equation where we got to this term T1 minus this term T2, and the negative y minus because of the minimum. That's why there is the minus here. And we'll get into all this in our discussion next Sunday. But since you asked, hey, how does the KL divergence, is that the loss? It isn't the loss, it's the function, it's part of the function that we will be optimizing through stochastic gradient descent in order to get good parameters for theta and phi, or stated more generally, in order to parameterize Q and parameterize P the best way in order to learn the latent variables and also to generate the x's given the latent variables, or to generate the latent variable given the x's, which is therefore this guy, right? This is the theta we want to learn, and that's the phi we want to learn. And in one case, it's, x given z takes us from the latent variable to x, and z given x takes us from the observed variables to the latent variables. And the other interesting thing, and maybe it was obvious to other people, but at least to me, going through the map and stuff and having him explain it, explains that in a variational autoencoder, right, you typically have, it's an autoencoder because you have an encoder first layer and then a decoder layer. But what is interesting is the encoder layer is actually the inference layer, and the decoder layer is actually our generative layer. Because the decoder layer is what takes you from the z, the latent variables, to the x's, which are, kind of our output. In a variational autoencoder. It's obviously the input as well. But the point is that that's what gets you to the x's. And the encoder is actually what you are inferring the z's given the x's. So this is the decoder. This is, this p theta of x given z is actually the decoder, and yeah, this guy is the encoder in a variational autoencoder setup.
Okay.
And we'll go through all this in our next lecture. And then, so what we, we kind of end up with this guy, T1 minus T2. So, this equation minus this equation as our objective that we are now going to optimize using stochastic gradient descent. And then we use two different, the next set of steps, he uses two different ways of getting to the same, one using Jensen's inequality and the other using just KL divergence. so that we are familiar with 3 different ways of getting to the same end result. Because as he correctly says, if you listen to any lecture online, video lectures, there are people who are deriving the stuff in one of the other ways as well. So this is the most general way that he has derived it, but there are a couple of other ways, and we'll cover those other ways in next Sunday.
Okay.
Any other questions before we call it done for this lecture? Okay, thanks everybody. Thanks for joining. See you all next week.
Thank you. See you next week.
Thank you.